Every single second, humanity creates an ocean of digital information. Every video upload, text message, and web search adds to a global network of data. Traditional computing systems process information linearly, step by step. But at this scale, that older architecture hits a wall. The sheer volume of incoming information is too massive for standard processors to handle. This diagram shows exactly why artificial intelligence is built differently. On the left, we see how humans learn through a linear timeline of experiences. On the right, AI learns by mapping millions of data points simultaneously, hunting for hidden patterns across massive datasets. By feeding these networks high-quality information, the system begins sorting and refining its own logic, autonomously improving its accuracy at specific tasks over time. All those searches and videos no longer sit in dormant archives. They act as the active fuel powering the processing engine of modern AI. Because AI systems can process all that fuel so rapidly, they have developed the ability to output entirely new material. Within seconds, systems can write essays, compose original music, or generate complex functional computer code. These same systems translate text prompts into high-fidelity visual artwork and realistic animations, constructing complex digital environments pixel by pixel. Designers, writers, and programmers use these models to iterate through dozens of concepts in the time it used to take to finish one. Yet mastering text, music, and pixels on a screen is only the preparation phase. The real test begins when this intelligence leaves the digital realm and steps into physical reality. To get AI into the real world, the software itself had to evolve faster. Today, developers use AI coding assistants to write code, find bugs, and test prototypes side by side. Removing the manual coding bottleneck allows for the rapid training of the neural networks required for advanced computer vision. Computer vision is the specific technology that enables machines to capture, process, and comprehend live physical environments through digital lenses. Looking at this simulated street view, we can see the system actively isolating moving cars, tracking pedestrian faces, and reading environmental text in real time. By charting these spatial relationships and predicting trajectories, engineers deploy this visual tracking directly into autonomous vehicles and advanced security networks. Giving machines a visual context bridges the gap between raw data and physical space, allowing them to navigate our environment safely. Once a machine can see its environment, it needs a way to interact with it. Engineers are now combining artificial intelligence, visual sensors, and machine learning to build robotic hardware capable of complex physical interaction. Rather than relying on rigid, pre-programmed loops, humanoid robots dynamically learn complex physical movements, adjusting their grip and balance while assembling intricate parts. In industrial settings, these intelligent machines already communicate with factory networks to execute highly specific, heavy-duty tasks with precision. AI now has a physical body capable of manipulating the material world. It sets the stage for a new level of human and machine collaboration on a global scale. To push processing power further, engineers are moving beyond smaller microchips. Quantum computing operates on mechanics completely divorced from traditional computing architecture. This diagram illustrates the difference. A traditional computer, shown as a linear binary sequence, tests one path through a maze at a time. The quantum model, represented by a glowing wave, maps every possible route simultaneously, solving simulations that would take standard computers thousands of years. Scientists apply this exact capability to scan dense biological data, isolating specific structural anomalies within human DNA. By analyzing genetic information at this speed, researchers can identify viable candidates for new medicines in a fraction of the time required by traditional trial-and-error laboratory methods. This application of AI and quantum biology shifts the focus from simple operational efficiency to solving complex life-and-death medical challenges. With machines learning to see, move, and solve complex biological problems, the concern about human obsolescence is natural. But at its core, this technology acts as an instrument for human amplification. The most significant breakthroughs on the horizon will require human researchers actively directing these AI systems to test hypotheses, process complex data, and solve novel problems. As seen in laboratories and on factory floors, the integration of these tools allows human creators to focus on strategy and problem solving, while the hardware handles the execution. Artificial intelligence is a powerful engine for processing our world, but its ultimate trajectory and the moral weight of its impact relies entirely on human intent.